The physical constraints are absolute. A 54,000-pound jet decelerates from 150 miles per hour to a dead stop on 4.5 acres, a distance under 350 feet. Simultaneously, on the opposite end, another jet accelerates to 165 miles per hour in 2 seconds. Normally, a Nimitz-class carrier maintains a baseline of 120 launches and recoveries every day. In surge conditions, that tempo climbs to 270 sorties per day. When pushed to its limit, a carrier sustains a rate of almost 1,900 flights in a single week. This operational pace is only possible through a strict systems engineering architecture. The Navy manages this through 3 distinct layers: the mechanical management of kinetic energy, non-concurrent spatial scheduling, and a redundant distributed control architecture. Operating in this environment requires reducing chaotic physical variables into predictable, repeatable mathematics. Beneath the flight deck, a series of hydraulic arresting gears handle the incoming energy. When a tailhook catches a wire, that cable pulls a mechanical piston through a fluid-filled cylinder. The piston forces hydraulic fluid through small orifices, converting the aircraft's kinetic energy into heat. This mechanical resistance stops a 60,000-pound jet rapidly and safely. The size of these holes is adjusted for every landing, calibrated specifically to the weight of the incoming aircraft and the prevailing wind conditions. The system then resets automatically, prepared to catch another aircraft in 45 seconds. Because the tailhook occasionally misses the wires, the landing procedure includes an engineered safety protocol called a bolter. Pilots apply full throttle immediately upon touchdown. If the wires are missed, the aircraft retains enough kinetic energy to climb away from the deck and try again. Launching these aircraft requires the opposite application of force. For decades, Nimitz-class carriers have used steam catapults to reach takeoff velocity in 2 seconds. The diagram on the left shows the steam system, where a pressure valve must be mathematically calibrated to drive a shuttle down the 300-foot track based on aircraft mass. The newer Ford-class carriers, shown on the right, utilize the electromagnetic aircraft launch system, or EMALS, which replaces the steam piston with a linear induction motor. Instead of using steam pressure, EMALS uses alternating magnetic fields to accelerate the launch shuttle. This shift provides faster regeneration times, more precise acceleration curves, and reduces the physical stress on the airframes during each launch. Moving from mechanical steam pressure to calibrated electromagnetic force extends the service life of the aircraft while increasing launch capacity. The ship avoids launching aircraft at random. Instead, flights are batched into 90-minute windows known as cyclic operations. This Gantt chart tracks a single event of up to 20 aircraft. The preparation follows a strict timeline: pilot inspections at the 45-minute mark and engine starts at the 30-minute mark. During positioning, the ship turns directly into the wind. This increases the airspeed over the deck, reducing the ground speed required for a safe takeoff. At the 0 marker, the launch cadence begins, firing 1 jet every 20 seconds from the 4 bow catapults. This timing creates a conflict for deck space. Returning jets from a previous event need the same landing area currently being used to stage the next group for launch. The architectural solution is the angled flight deck. By positioning the landing strip at a diagonal, the recovery zone stays clear of the parked aircraft and launch catapults on the bow. The combination of the angled deck and cyclic scheduling creates non-concurrent sequencing, a necessity to prevent overlapping launch and recovery events from becoming a collision risk. Macro-level coordination happens below the flight deck in the Carrier Air Traffic Control Center, or CATCC. These controllers manage the airspace using radar, often without ever seeing the aircraft. As shown in this airspace visualization, CATCC sequence incoming jets into a Marshall stack, a tiered holding pattern orbiting the ship at different altitudes. Aircraft hold at these precise intervals until it is their turn to break from the stack and begin their final approach. Primary Flight Control, or BOSS, has absolute authority over all aircraft within a 5 nautical mile radius. Down on the flight deck, 150 decibel jet noise makes radio or verbal commands impossible. To manage hundreds of sailors in real time without speaking, the Navy uses a visual, color-coded jersey system. Yellow jerseys are the aircraft handlers. They act as the deck's traffic police, using hand signals to guide jets into their exact launch positions. Green jerseys operate the catapults. Red jerseys handle the ordnance, and crash response teams stand by. White jerseys include the landing signal officers, or LSOs. They stand at the aft end of the ship, visually monitoring the glide path of every jet as it approaches the wire. The LSO has the independent authority to waive off any landing they judge to be unsafe, no questions asked. This hybrid model, centralized radar planning combined with decentralized color-coded execution, is what allows the deck to function safely at speed. The 1,000 flight per week tempo is the result of integrating mechanical physics, spatial geometry, and human control into a single seamless machine. This top-down comparison shows the latest evolution of this integration. The new Ford-class carriers feature a 33% larger flight deck and successfully completed over 8,700 EMALS launches during a single deployment. Increasing the deck area while utilizing advanced automation like EMALS directly improves the sortie generation rate. These new systems also increase human efficiency, allowing the carrier to operate with 900 fewer sailors than its predecessors. Sustaining 1,000 flights a week without a catastrophe is the real-world operational baseline of the United States Navy. The noise and movement on the deck are the outward markers of a rigidly disciplined logistical system, and one of the most successful applications of operations research and modern engineering.